When an archer draws a bow, they put energy into the bow, and that energy gets put into the arrow when they release the string. So Zachary, why don't you draw your bow? So when an archer draws the bow, initially there's not very much force until it's pulled all the way back, and then there's a lot of force. Now that force depends on how far the bow's been pulled back. And there's a function that describes that, the amount of force as a function of position. Now, depending on the type of bow, that function is different. Certainly, certain bows you have to pull harder, but other bows, the force doesn't change linearly with the amount of draw. So this bow, the force mostly depends linearly on the draw. This bow is a compound bow, and it works a little bit more differently. So Theodore, why don't you slowly draw your bow? So when he starts to pull back, the force increases linearly. But there are these pulleys and cams. And so as he pulls it a little further, going a little further, the pulleys come out and they reduce the amount of force that he has to pull to hold it. So now here he's pulling with a lot less force than when the cams were up at the top. This makes it easier for you to hold that bow, and it allows you to take a much stronger force than you would otherwise. So the point is, the different kinds of bows have a different amount of force as a function of draw, how far they've been pulled back. You can relax the bow. And so that will tell you how much energy. The integral of force as a function of draw tells you how much energy has been put into the bow. We can compute that with an integral if we know what that function is. And then that amount of energy, if it gets turned into kinetic energy, moves the arrow.
Okay, so different bows have different amounts of draw weight for different amounts of draw. And I said that that's a function. So let's examine what this might tell us. So let's plot what such a function might look like so we can get an idea of what we're working with here. So we have force as a function of draw. Let's say the draw I'll represent with x and the force I'll represent with f. Sounds easy enough. Okay, so let's see here. For not much force, we should get not much draw, and vice versa. If there's no draw, there should be no force. So this function, whatever it is, has got to start out on the origin. And as we start to draw the bow back, the force goes up. And maybe, if it's one of these compound bows, that force will decrease. Okay, so this could be the force function, f as a function of x, for some bow. And it's a physical fact that if I were to take the area and examine the area, that's the energy stored in the bow. Now, it's handy to have a way to represent the amount of energy as an area and represent the area for some arbitrary function, something that's going to involve the x and the f in some way. And have some notation for this. We're going to spend a lot of time thinking about this kind of construction. And so let's develop some notation for what this is. Well, in order to do that, we need one thing to realize is that this area function has got a start and an end point. It starts off at 0. That's where you start adding energy. And it ends at some particular point, let's call it A. That's where you stop pulling the bow. That's your A for anchor, your anchor point. And so the notation for this is called a definite integral. And the definite integral is an area, and you write it with this funny shaped S. And this is the function you're finding the area of, and the dx kind of signals to you that the independent variable is x. Let's break it apart and talk about it a little bit. This is a differential. Really, it's signaling to you that the independent variable is x. And this f thing here, the expression that you're finding the area of, is called the integrand. This guy is the start, and this guy is the end. Sometimes we'll call the start, we'll call that the left endpoint. And sometimes the end we'll call the right endpoint. And sometimes it's very helpful. I often suggest that if there's any possible confusion, just write x equals here so that you don't forget what the independent variable is. Okay, so if we know what this function is, we should be able to find what the area is, the amount of energy. Now, a little bit of units here. The draw is x in, say, meters. The force is F in newtons. And the energy is in joules. Okay, so that's a little bit about units. Now, actually, I don't have this function really because I have to measure it. I can only measure the draw and the force at a certain finite number of points. I can't measure it everywhere. That's just not possible. It's not practical. So what we can do is we can kind of break it up into pieces. So how does that look? Well, instead of getting everything, all this full area here, instead what we'll get is we'll get something of an approximation. And here's the way the approximation goes. For instance, if I'm looking for area, I need to break it up into areas of things I know. Now, I think everyone pretty much knows the area of a rectangle. It's base times height. So let me break this up into a bunch of little rectangles. Now, of course, as you probably can see right away, I'm missing some area. There's some area that I'm not getting. And I'm aiming here, let's say, for an underestimate. So you'll notice all of my rectangles are below the curve. That'll give me an underestimate. Of course, if I wanted it above the curve, well, then I'll get an overestimate. So all of these little wedge-shaped regions, they're not quite triangles because their tops are potentially rounded. Well, I don't actually know, but probably they are. All of these little red regions constitute error, a difference between the area of all of these rectangles added up and the actual area, the actual definite integral. Okay, but we can kind of say that what this ends up being is that the area is approximately, well, base 1 times height 1 plus base 2 times height 2 plus, well, a whole bunch more in there, up to, let's see here, how many rectangles do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe the last one's 10. Let's say there's 10 of them. So each one of these is a base times a height. Now, I've chosen all my heights to be different. They're telling me the amount of force, but the bases are all the same width. So base, I could say they're all the same. Height 1 plus height 2 plus lots more things, dot, 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 plus height 10. This will tell me an estimate of the amount of energy that's stored up in this bow. And that's an underestimate. If I wanted an overestimate, I could get that. How would I get that? Well, make sure that each of my rectangles are above the curve. Sometimes it can be a little bit tricky to figure out if you've got an under or over estimate. Okay, so I need this curve for our bows. How do I get this curve for our bows? Well, let's head into the workshop and take some measurements.
When a bow maker is designing and making a bow, one thing they want to know is how much force the string will put on the arrow. The force increases as the string is pulled back further. This tool is called a tillering stick, and it has gradations to tell you how far back the string's been pulled. The bow maker uses a scale to measure the amount of force on the string as the string is pulled back further and further. And so you can record the amount of force as a function of the draw, how far the string has been pulled back. That function depends on the different kind of bow that you have. So this particular kind of bow has a different function that describes its draw weight as a function of the draw. Another bow would have a different function. We can find the amount of force on the arrow at any point along that function, and we can overall find how much energy has been put into the bow, into the limbs of the bow, to figure out how much energy gets put into the bow.
Okay, so the results are in. These are the force curves for the two bows that we saw at the beginning of the video. The blue one is for the longer bow, and the red one is for the smaller compound bow. You can see right away that around an extension or a draw of about 30 centimeters, or 0.3 meters, the compound bow drops in force. That's as the cams have engaged and made it a little easier to pull that bow back. It also actually, if you keep pulling a little bit farther than you're supposed to, the force goes up rather dramatically. The other bow pretty much increases linearly as you pull it back further and further. And actually the typical working draw for that bow is about half a meter. So at that range you get about 120 newtons of force. Now I won't bore you with the details of adding up the amount of energy, i.e. the area under each curve, but if you add up all the little rectangles, for the blue curve you'll definitely get an underestimate, because if each of the rectangles there, you'll find the height, and each rectangle is a little bit less than the region that comes next, because it's increasing. That function is monotonic increasing. So if you use the left endpoint to find the height of each rectangle, you'll be a little bit too low. If you want an overestimate, you could use the right endpoint to find the height of each rectangle. For the compound bow, it's kind of difficult to tell whether you'll get an over or an underestimate. You'll get some kind of estimate, and it probably won't be too far off. And of course, if you wanted a better estimate, you could take more measurements. That would work just fine. Okay, well, let's focus our attention on the blue one for the moment, the long bow, the one without the cams. And for that bow, when we draw it back at the very end, you get about 50 joules of energy stored there. On the other hand, if you pull it back to its working amount, you get about on the order of about 30 or so joules. Okay, so now given that amount of energy, we can use a formula for kinetic energy to figure out how fast the arrow goes. So saving you the trouble of adding up all those little rectangles, I just used a spreadsheet to add them up. When I do that, I find that the long bow had about 32 joules of stored energy, and the compound has about 19.6 joules of stored energy when you're about ready to release the arrow. Okay, so how do we translate that into speed? Well, we make a little bit of an equation, and it's optimistic. It assumes no friction. Is that at the point of release, all that stored energy gets turned into kinetic energy. Energy of motion. Now, the formula for kinetic energy is 1/2 mass times velocity squared. Okay? And, all right, fair enough. So if I have 1/2 mass times velocity squared, and that is going to be equal to this integral from 0 to the anchor point A of x dx. Well, now I can just solve for the speed. That's pretty easy to do. Okay, so the velocity is this square root expression. All right, well that's not so bad. So we can go ahead and compute that. We now know how many joules are there. How heavy is a typical arrow? Well, a typical arrow is about 16 grams. Now, since I'm doing everything in SI standard units, that's 16 over 1,000 kilograms. And you really want to work with joules and kilograms. That way your speed, your V, will be in meters per second. Okay, so when we do that, when we take the mass for these, we find that the speed for the longbow is V equals 2,000 over 16 times 32 square roots. And if we do the speed for the compound bow, still the same 2,000 over 16 times 9.6. Oops. Okay, so what are those? Well, this one's about 64 meters per second. And this one here is about 35 meters per second. Okay, doesn't sound too bad. Let's go see how we did, because this is an estimate, and this is an optimistic estimate, because I assumed that that the kinetic energy is equal to the stored energy. That's no friction. And of course there is some friction, so our actual speed will be a bit less. So how do we measure the speed? Well, one easy way to do it is just to take a video of the arrow being fired and count how many frames the arrow was in flight. So that's not too particularly difficult. You just need to set up a safe place to shoot an arrow and videotape it. So let's do that. This video was taken at about 30 frames per second, and it took about 7 frames for the arrow to fly. So 7 frames, 30 frames per second. How far did it go? It went about 10 meters. So how fast did it go? Well, speed is distance divided by time. That's 10 meters divided by 7 frames times 1 frame. 1 second. 30 frames. So that works out to be about 300 over 7 meters per second, which is about 42 meters per second. A bit less than the 64 that we had estimated, but that's probably due to friction. And 7 frames isn't very much, but not too bad for some basic calculus. What we'll be doing next, of course, is trying to improve these sorts of things, improve these sorts of estimates. But in order to do that, you need some better knowledge of the functions. And that's a little more theoretical, but it's really basically the same idea. Well, thanks for watching, and we'll see you